IFT Colloquium. So today's speaker is Mario Chavez from CNRS in France, and I can see Sorbonne University as well. So as usual, I'm going to introduce a little bit his background. So he's an expert in complex systems applied to neuroscience. He did both the master and the PhD degrees in France, and then he got some postdoctoral positions in France and in Italy, in particular in Florence. And then, at the time he was working in the field of nonlinear physics and biomedical signal processing. And then he came back to France, where he became a permanent researcher at the CNRS, indeed. His research activities concern new methodologies for characterizing functional connectivity of electrophysiological signals. And he has developed a complex network-based framework to quantify the functional interactions between different neural structures. And today's talk is going to be, I would say, about that from the title. And the title is Hyperbolic Embedding on Multilayer Networks. So, Mario, the floor is yours.
Thank you very much. Thanks again for the invitation and for all of the students and colleagues that are present here. So we have already met yesterday. So today I will present the last, my current field of research is the representation of complex data on geometrical spaces, not necessarily Euclidean. And so this is the last work that we have made with my former PhD student, Martin and Alice. Okay, so multiplex, multi-layer, multi-networks, it's a framework that allow in the last probably 10 years, allow to understand better or to have a more complete view of a connected system, which is the idea. For instance, probably the best example comes from the social networks. You interact with some of your colleagues, some of your friends through social networks, but also probably you interact also physically, not virtual relationships. But probably you may have also familiar links with some of them. And so there has been some colleagues that have shown and have provided a new framework to study these multiple interactions of the same elements, and in some cases provide a more complete view of the system. And of course, it has some interesting properties. So other, for instance, colleagues have represented the different air transportation systems, where they consider each layer corresponding to the different flights, for instance, for the companies, Ryanair, Lufthansa, EasyJet, and so on. And in some cases, again, this representation allows to understand some phenomena, spreading phenomena, for instance, in the case of transportation. And of course, as you can imagine, in neuroscience, my main field of research, we are not the exception. But here we have different ways to build a multi-layer. Multi-layer in the sense, for instance, sometimes, as I explained yesterday, we may have access to different neuroimaging modalities, magnetoencephalography, electroencephalography, functional magnetic resonance, and so on. And we can build a network or estimate a connectivity network with this data. And so we can imagine that we may have a network corresponding to each neuroimaging modality. Another way, for instance, if you can estimate a connectivity matrix for different frequency bands of the EEG signals. Yesterday I explained to you that the EEG, the neurophysiological signals from the brain are, by definition, has been studied in some frequency bands that have Greek letters, alpha rhythm, beta rhythms, and so on. As I mentioned it in the last year, there has been a very nice review. I think I don't forget any of the main reviews. So there is a rich literature to how to characterize, how to study, why is interesting this representation, the impact of this multi-layer structure on the dynamics. So a very complete study, the mathematical formulation of multi-layer networks. Do you remember all the parameters, network parameters that Johan explained? Degree, clustering index, shortest path, centrality, and so on. So Manlio and his colleagues extended this to the multi-layer cases. But I don't like this approach. Why? In the case of neuroscience, okay? Probably for transportation is another thing. At least for neuroscience, generally, in the last 2 days, we have discussed it with some students, and we have talked about a classical problem with the characterization of brain connectivity networks. And it's the following. You have now a rich literature, different parameters, let's call it theta, different parameters, and which parameter is the best parameter to characterize the network. I remember yesterday one of the questions to Johan, I think, was, or for Anna, probably, which is the best parameter to study networks? You have hundreds of parameters to study. So, in neuroscience, I repeat, the idea, I mean the objective, is generally you have a group of patients, or group of healthy subjects, or 2 groups of people doing different cognitive tasks, sleeping, awaking, and so on. And so you want to identify some nodes that differentiate both conditions or both brain states. So if you are lucky, probably you will find a subset of parameters, network parameters, clustering index, degree, centrality. And if, again, if you are lucky, probably you will see a very clear separation. But I mean, this is a problem for engineers, probably. You test 100 parameters, and then I don't remember one of you explaining that his vector were 70,000 parameters. I don't know how many. So for me, it's too much. And I don't like it this. So instead, I prefer to use this approach, the graph embedding techniques. Which is the graph embedding? The idea is to project, to map the graph, which is very abstract concept. For instance, here in a graph, if I ask you which is the mean node, the average node of this group of nodes, it's very difficult to, it's not defined. So which is the variance of the blue nodes? I mean, in the graph space, unfortunately, is not defined. But if you do an encoding function, a good encoding function, you can map this graph onto an embedding space. You can imagine Euclidean, and it's magic, because here you have a metric, you have different distance, very well defined, and you can, for instance, estimate the average node for the group of blue nodes, or the variance in terms of the distance. So the idea of this embedding or encoding function is that you will respect the similarity in the embedding space, I mean the distance in embedding space, but will approximate the similarity in the original graph. So which are the advantages? Yeah? Yes, I will. I will arrive to this. So this approach has some advantage, is that sometimes, depending on the function, depending on the embedding space, you may encode simultaneously many of the network parameters. So for instance, the shortest path length currently used in graph theory sometimes can be related, theoretically related, to the distance on the embedding space. The clustering index in the graph space is the number of triangles that you can measure on the network. Of course, here is related also to the closeness of this group of points in this embedding space. I will come back. Yes, here. So, which is the classical representation of brain networks? For instance, the brain networks, how can I define a node? A node, for instance, in the case of functional fMRI, is each voxel where I can measure a time series. In the case of the electroencephalographic networks, I mean, each node is each channel, each time series. The record position where you get the time series, this is currently defined as a node. Yep. In case of fMRI, you don't need electrodes. It's immediately, you make an estimation, and you have a different time series, probably dozens of time series. of different box cells. Box cells is a cube, imaginary cubes for sure, inside the brain. And so you define your nodes, and you can, it's an estimation, of course. Again, I repeated yesterday, it's an estimation. For instance, the classical representation considers the following. You have the normal brain network, and the network neuroscience theory assumes that some diseases are related to brain perturbation. For instance, on the stroke, there is probably a node, a failure in the node, a failure in one link, or a failure in a group of nodes or links that are responsible of the stroke. Or, for instance, the seizure is very well known that epileptic seizures are sometimes related to a failure on the connectivity structure of the brain network. But the classical representation here in Euclidean space very often is not enough to distinguish both groups. But my group and with some other colleagues, we have shown in different works that using something latent space, I mean the embedding in other geometrical spaces, where you can perfectly distinguish this. I will come back later, and I will show you the importance of this. Yep. Yes. Let me go further into one slide, and you will see it immediately. So, and which latent representation, which geometrical non-Euclidean space, with some colleagues, we have decided in several years to study hyperbolic geometry, hyperbolic manifolds. I suppose that here at the IFT Institute of Física, you are very familiar with the gravitational theory, which is defined by definition hyperbolic. But I will, if you are patient for 2 or 3 slides, you will see that you can map the nodes of the graph onto different manifolds, hyperbolic manifolds. There are different hyperbolic manifolds. There are different hyperbolic spaces. The most famous or the most well-known are the hyperboloid. Of course, the Poincaré disk, as a French group in France. We generally work on the Poincaré disk, and vive la France. And so, but some colleagues in Barcelona, they use something called the native representation. It's kind of hyperbolic disk, but not bounded. The Poincaré disk is a radius 1. Now, your questions is, okay, how can I pass, and why this stuff? Be patient, I will come back. So why hyperbolic geometry? Why? Okay, the hyperbolic geometry has very nice properties. And for me, I mean, at the beginning, I'm engineer, telecommunication engineer. So I learned, and I suppose that most of us, that the sum of the angles, internal angles of a triangle is equal to 180. So I was very surprised to learn and to discover that in the hyperbolic geometry, this is not the case, but also that the circular circumference can be larger than 2p radio. So, wow. But this is only a curiosity. What is interesting, and this is the key point, is that on the different hyperbolic manifolds, you can associate a metric, and of course, you can define a distance between points, which is, of course, the distance, for instance, in the hyperbolic, in the hyperboloid. This is a point, one point A, one point B. The distance between these 2 points is not a straight line, as in the Euclidean space, but it's an arc, a paraboloid, and you can calculate it by this function. Even if you see it complicated, there has so many interesting properties, practical properties for the analysis of data that I will show you. But okay, I always been curious, okay, this is probably a mathematical stuff that, okay, I don't know if it exists, but I was very happy when I discovered that the hyperbolic space is present also in nature, and it has very nice properties. So probably, I don't know if in Brazil you know these plants, typically from Christmas, with the very red beans during the Christmas, and of course, these salad leaves that most of us we know. So it has been proved that the curvature, the form of the leaves are hyperbolic. That means they have a negative curvature. Why? Why this? Okay, this negative curvature allowed to these plants to increase the surface area. And he says increase the surface area for a given volume, they are available to absorb more light. In the arts, probably you know this Dutch artist, Maurice Escher, who is very famous for the use of hyperbolic geometry. And this is an example of what the difference of between two. For instance, here you can observe a group of red and white horses. There are two colors of horses. You can see all the horses are the same size. Here we are in the Euclidean space, but the representation of these horses onto hyperbolic one, you can observe that at the center, the horses are larger, but as we come closer to the peripheria, the horses becomes more and more smaller and smaller and smaller. But given the distance and the metric endowed to the hyperbolic geometry, the distance between these two small horses are the same or equivalent between two. But which is the advantage is that the hyperbolic, you can represent infinite distance, I mean very, very large distance, in a very compact way. How? Okay, this is a curiosity. If you like this artist, there is a very nice paper in the art journal, Leonardo, which explored different aspects of this drawing in particular. Circle limit number 3, which is this, and if you are interested on the mathematical property and the relation with art. So, curiosity. So, as I mentioned, the Euclidean space, imagine you have a tree, a very large tree, in the sense of graph, not a tree, green tree, but a graph. For instance, for those working with very huge databases, sometimes you have the structure of the database is organized as a tree, and you have a very, very large tree. Okay? And the distance between the root and the last leaf probably are very large. So if you want to represent this into Euclidean space, you need probably you need a lot of dimension in the Euclidean space, but probably also it's not easy to visualize. So, in contrast, because the hyperbolic geometry, I will explain it, I promise, how to project into the hyperbolic space, you can represent this very large distance in a compact way. I mean, a disk of radius 1. So visually can be nice. And further, some colleagues in Barcelona especially, they have proven, they have shown theoretically that many properties observed in real complex networks, scale-free, clustering index, and so on, can be explained by the relationship of the nodes in this hyperbolic space. So the advantage is a compact representation of very complex data, but also that you can model the generation of networks directly, and sometimes there are colleagues that do link predictions. So it's not a problem. So let me only to mention another point that will be useful for the result that I will show you later, and is the following. So in statistics, I think for me, statistician, engineer, the basic distribution is the Gaussian one. So, okay, basic but okay, I can imagine the Gaussian in a linear, I mean, for a scalar variable, but if you have phases, how do you define a Gaussian for circular variables? So I have a bad news, is that for the circular variables, the function, the definition of a Gaussian function is this one. So where this term is a modifiable Bessel function of the first kind. Okay, probably for the mathematician, they will be very happy, but for an engineer, and for especially working with brain data, I don't like very much this. Oh, it can be complicated. I mean, even if Python, Julia, Rust, whatever, they can deal with this kind of data, in my group, we try always to understand and try, I have some problems with this kind of representation, but we can do an approximation. As an engineer, we always love approximation, And for instance, if you have the data, here is I represented the data. You can see that there is a density, a higher density of points or circular variables located on the left side of the circle. So, but you can project on a tangent plane, and on a tangent plane, I can apply any statistic defined with Euclidean distance. So, and the definition of the Gaussian function is the classical that all of us use very often. But of course, you can project this red curve, come back onto the circular manifold. In the case of a spheric manifold, you can see here the representation, a toy representation of the Earth. As I mentioned it, the distance between 2 points is not a straight line anymore. Of course, I mean, if we take the plane, all of us, we know that the plane will do the shortest distance between 2 points is this one, because we cannot traverse, we cannot go through the Earth. But if I want to estimate a function, sometimes I can use this projection on the tangent plane. But what about the hyperbolic manifolds? And the hyperbolic manifolds, fortunately, you may estimate or define a tangent plane in any point of the hyperboloid or even of the Poincare disk. So this is with the exponential and logarithmic operators, matrix operators. I mean, with the logarithmic matrix operator, you can project data from your hyperbolic manifold onto the tangent plane, and you can do your favorite statistical operation on the tangent plane, and if you want to represent it on the hyperbolic disk or hyperbolic manifold, you can come back by using these expressions. Yep.
So when you project the data from the discrete data to the continuous space,
yep.
in the discrete data, only certain points are connected, right?
Yep.
But in the continuous space, all points are connected.
Yep.
There is a distance between all points.
Yep.
So how do you know that this projection will always preserve that connectivity that you have originally in the graph?
Yes, this is a crucial point. Let's say, for instance, if we have a circular manifold, if I have my points located here, I can define a tangent plane here and project. There will be an error, as I said, it's an estimator. Okay? There will be an error, and I can consider that the distance here is equivalent to the distance on the manifold. But a very good question is that what happens if I have data located here and I projected here? We have a problem. There will be an error, a very last error. So this is a kind of trade-off you must do. I mean, there are some operations to ensure you that the tangent plane where you will project the data will be the best approximation to the discrete data. Here I'm talking about only discrete data.
My problem is that, so for instance, you have 3 points.
Yep.
And one is connected with the other. Right?
Yep.
So now you put this in a continuous space. Now the 3 are connected.
Yes. Imagine, even if.
How do you know that in this projection,
Yep.
how do you know that the geodesic is the right one
Yep.
that connects the right point?
Yes. Okay. Yes, I understood the question. And imagine that even if you don't know up to now, you have a graph that you projected on a circular space. You have the nodes, probably here and here. But once you project it here, you forget more or less the connection, because you know that if your embedding function of the graph, if it's well built, you know that the distance on the manifolds will be equivalent to any distance that you can define. For instance, the diffusion distance or the shortest path based distance defined on the original graph space. So you don't need here, once you projected the nodes here, you don't need have this, because it has no sense.
Well, for instance, in this graph, these 2 nodes on the right
Yes. Yes, yes. Let's say it was not the best example, but this will be, here you have the two groups of nodes. The red nodes are closer by, even if you don't know anything about graph theory, you can intuitively, you can see that this group of nodes are closer, are more compact. I mean, compact not in a mathematical sense, but in a visual sense. And this group of node blue are also and form a separate group. So, and again, if your function is correctly done, you will obtain something like this. The blue nodes will appear closer, separated of the red points that also be closer. And the distance on the embedding space using the metric endowed to this embedding space, Euclidean distance or hyperbolic, if you do, is related to the distance, for instance, the shortest path or the diffusion distance on the graph. Yep. And yes. The points here, there is no link point. There is no link between the points anymore. There is only a distance. And the distance you... no. No. The distance is not
also in the graph,
connection.
they are all connected. You just go via different nodes.
Exactly.
There is not a direct connection, but there is an indirect one. And I think what he's claiming is that the direct distance in the embedding space is similar to the indirect distance following the graph. The embedding function is built in such a way that computing the indirect distance passing from point to point to point is similar to the direct distance in the embedding space.
So you don't need to have a link here saying, okay, look at, I understood, for instance, that this point is not connected to this one, right? And here, probably, this point is this one, and this point is this one. And the Euclidean distance between these 2 points are larger than between these 2 ones. So that's the only connection on the embedding space. So this is an example of what you can obtain with...
My question is that this function that you use to embed
Yep.
has an inverse.
Yes.
So you can take this point and you will...
Not for all the encoding function. Not for all the encoding function. For the diffusion embeddings, I mean the Laplacian maps embeddings, yes. But for the hyperbolic, no. There is no that you cannot come back to the original graph space. No. So imagine that I have points, if you want, the nodes of graph projected on the hyperbolic disk and the Poincaré disk, and I project them onto the tangent plane. I estimate the Gaussian, and the Gaussian, I reproject, I mean, all the points of the Gaussian. Now I can increase the resolution. I can make a grid on this Gaussian on the tangent plane. I can reproject it back. And you can obtain something like this, a kind of banana, kind of bean, representing the Gaussian of this point. So the example of application that will be used here is that we can obtain the distribution, for instance, of a given node. We can concentrate on the same node from different networks, from different patients, from different layers, okay? So this is the work of my former PhD student. Now, how can I pass? There are many embedding algorithms. Some of them we have discussed about, north to back, Laplacian maps, and also even for the embedding, for the mapping a network onto an hyperbolic manifold, there are at least 20, probably 10 different methods, and every method claims, I'm the best. I'm the best, I have the minimal error, I have the minimal error, okay. But as an engineer, I like something more data-driven approaches that provides good results. Probably are not the best approximation to the graph. Probably there are another embedding method that provides less error, okay? The error in the sense that probably the nodes on the embedding space, the distance between the nodes are slightly larger than the distance on the original graph. So. No, no, no. Yes, for the diffusion maps that maps a graph, the nodes of the graph, onto an Euclidean space, the approximation depends on the number of eigenvalues of the Laplacians. So of course, if you take all the eigenvectors and all the eigenvalues, the error in principle is close to 0. Of course, numerical error, but close to 0. So, but this is only when you project with the Laplacian maps onto an Euclidean space. But in the hyperbolic, no, there's no 0 error. Yes, yes. And I will use this property, you will see it. I will use this this property to studies in neuroscience, okay? So, imagine that you have a graph. You can associate a weight to the link. Probably you already have the weights from the links estimated, I don't know, with correlation, synchrony, nonlinear correlation, etc. So at the end, you will obtain a weighted networks. In the statistics and machine learning literature, it's not nothing to do with physics, but machine learning, you have a huge literature about how to project this kind of data represented as a graph, and to project them in a low-dimensional space. So probably some of you are familiar with isomaps, Laplacian-based as diffusion maps, but in general, any kernel-based methods that can do the right thing. So now, we can project the different nodes of the graph onto a plane, two-dimensional plane. No complex, no complicated. There is an error, yes, but I assume I'm tolerant. Now, this algorithm, the coalescent embedding method proposed by some colleagues several years ago, there is the following. Once you have the data on the plane, you rearrange the nodes, the points, on a circular. Now, respecting the order of the points. You can see here I put yellow, orange, red, and blue. So you respect more the order of the points here, and you project, you rearrange these points on a circle, respecting the order. And then you associate the radius in this way, where this index is the rank of the node in the sense of the number of links that the node has in the original graph. And Muscoloni and colleagues proved that this is an efficient and relatively correct, I mean, with an error that can be tolerated between the hyperbolic Poincaré disk, the distance between hyperbolic Poincaré disk, and the distance, especially the shortest path, that you observe or that you can measure in the original graph. This, you put here the body center here. No, once you have the point, the data, the projection on the two-dimensional plane, you select the body center, and you project, you make a circle, and you project all the points onto a circle. The body center. The center of mass of all these points. So, and probably you were asking, okay, but is it necessary to embed, to use this hyperbolic geometry for the brain data? Why? Are you sure they cannot? Because there are some papers already using Euclidean, I mean, projection on the Euclidean space. So, and let me show you what we have found recently with my students. We had an anatomical network, as I mentioned it yesterday, refers to the bundle of the fibers that connect the different brain areas. So it's something that you can touch. It's anatomical, it's physical. The physical connection. So here I have a physical network, but also I have a network reconstructed and estimated from the time series, measured on the same points, on the same brain areas. I represented here the nodes located on one hemisphere, and red the points or nodes located on the other hemisphere. So here is a representation using the favorite software, working with networks. But using diffusion Laplacian maps and Euclidean projection onto Euclidean plane, look at, for the anatomical network, you observe, you respect this separation of hemispheres. Very nice. I mean, it's the minimum thing. You know that the nodes are separated on a natural space, the brain. What I was expecting was to find the same separation. But for the functional networks, it's not the case. You can see there is no clear separation. Probably, I would need a higher dimensional space to separate it correctly. But at least on this low dimensional space, I cannot. But look at what you obtain when you project onto an hyperbolic manifold. The nodes are perfectly separated. I mean, you can observe perfectly the separation of the hemisphere for both the anatomical, but also for the functional one. So, message, if you work with an anatomical network, don't be complicated, and you can use projection on the Euclidean space. But if you are using or working with network estimated from time series, it's probably better if you use another projection. In this case, for our case at least, was the hyperbolic one. So let's come back to the multi-layer stuff. So as I mentioned, we have the brain. We may have different layers. The different layers can correspond to different frequency bands. I mean, the interactions at the different frequency bands can be different subjects or patients, the network from different subjects, can be the network from different neuroimaging modalities, that mean different data, or, I don't know, you may have a temporal network that changes with time, and probably you may construct the layer, each layer for each network at each snap time. Okay? So now here you have two possibilities. You may have independent embeddings of each network and then try to combine them by your favorite statistical tool. Or what we have done is to do a joint embedding, probably, and to see, you will see what happens when you do this independent embedding. You can imagine that I will show you that the joint embedding, the multi-layer embedding, the embedding that takes into account the information on the different layers, provides a better representation of the system. But be patient, please. So we started from the same coalition embedding approach. Imagine you have three layers, green, red, and blue. You have the three connectivity matrices, red, green, and blue. And now you can build a supramatrix in this way. You organize your matrix in this way. And here, you use a mathematical trick. You put the identity matrix, multiply it by a factor. I will come back in 2 slides more on this factor. Then you embed, you apply your favorite nonlinear dimension reduction method to the whole supramatrix. Okay? Again, you can separate it. I can keep the nodes in blue, the nodes in green, and the nodes in red are mixed here, and I can separate them, and I associate them to each layer. And again, I redo the same thing as the coalition. That means I associated a radius with a slight modification that is here. The data are here in this paper. And if you are interested, we put the code available. But at the end, I will repeat the details of the code. So let's see a very sample model to show you if it works or not. Here, for that, I used a multi-layer stochastic block model. It's a very nice model. I consider only a network with 3 layers, each layer with 3 communities, 3 groups of nodes, represented here in green, yellow, and violet. You can control the probabilities that links the nodes inside each layer, but also the probabilities of a connection between the different layers, okay? And see, if I use individual embedding for each layer, see, you can check here that the colors of the communities are mixed. So if you use the individual embedding, I mean, you concentrate on a single layer, you embed it, you cannot distinguish the groups. The same problem as for the functional anatomical. You cannot distinguish. In contrast, by using our method, I mean, building this supramatrix, embedded supramatrix, you can observe this clear distinction. And an interesting point of this approach is that you can also apply it when your networks have different size. For instance, here we have simulated a network. The first layer have this number of nodes, and the third one was slightly smaller. Of course, we cannot test it extreme case, for instance, 100 versus 10. We have not tested. But okay, in neuroscience, at least, this is something, I mean, is similar to what we can encounter when we analyze real data. And again, you can see that you can perfectly get the community structure, the cluster of nodes presented in the original space. So, which is the effect of this parameter? As I mentioned, so for that, we have used it only to illustrate. We have used it not 3 because it was complicated to illustrate, but 2 layers, okay? A very small networks. And which is the role of this parameter mu? You can see that as mu becomes larger, you will force the embedding of the 2 layers to become more and more similar. If the network red and green are practically identical, and if you put a very large mu, the nodes projected, the green nodes projected, and the red node projected will be practically identical. The position on the embedding will be identical. So, but okay, large enough. How much large enough? Sorry? Yes, that's the next slide. Is the next slide. But mu, you can measure it. You can extract it from data. You will see. So how can I measure this displacement, this difference between the 2 projected networks? Imagine you have here a network with node orange and blue, and these are the 2 nodes with the same index, the node E. So as I mentioned it, you can use your favorite hyperbolic distance, this between the 2 nodes, and then here you can average, you estimate the average or the mean hyperbolic displacement of nodes between the 2 layers. This is what I call it G-score. And now, when you consider 2 networks, 2 layers with similar connectivity, similar, not equal, but similar, you can observe that here we have modified this mu value, these mu parameters, and in color you can encode the error. How different are the 2 embedding, the 2 layers projected? And you can see that there is a very nice separation of this. Once the mu value is larger than a given, and this is the mean edge weight. I mean, here we control it also we have tuned, we have tested different situations, different conditions, by modifying the weights of the nodes. But the plateau of the error is reached when this mu parameter is larger or equal than the mean edge weight of the network. And this, you can measure it on the original graph. So in the method, you can, for the method, you can measure this. You can put it on the supra matrix and then embed. But also, it works if you have two layers very different. As you increase the mu, you will force the two embedded to be more and more similar. But of course, they will never be identical, because at the beginning, they are different. So the error will never be close to 0. There is a small error, but again, the plateau is reached again when you reach this value. So how can I test it here in neuroscience? So here, as I mentioned yesterday, I mainly work on epilepsy. And in epilepsy, as I mentioned, there is a theory that states that probably the generation and the propagation of seizures is facilitated by the anatomical structure and the anatomical connection. So you can imagine the roads, and if there is a very large propagation, a massive circulation of traffic, is probably because the roads are designed in a given way. So sometimes for those patients who has a lesion, is something related, it's called the structural lesion. They are concentrated, for instance, in the temporal lobe epilepsy. And then you may have other areas, surrounding areas, that all of them are responsible of the generation and propagation of seizures. But only to test, to validate, and to see what the method is able or not to do, I wanted to identify if the method could identify brain areas with the aberrant connectivity that facilitate this seizure. And for that, I used this data. I used anatomical networks, diffusion MRI. Here again, a kind of picture of the network obtained from one patient. So you can see there is a kind of problem here. So we used data from this number of patients, but also we used data from healthy subjects. From the patients, for this population of patients were more or less homogeneous, all of them suffered from temporal lobe epilepsy, a lesion on the temporal lobe epilepsy, not necessarily the same brain areas, because no, we are not so lucky. All the patients that arrive in a hospital, they have lesions in different points of the brain, but we selected a group that had a lesion on the temporal lobe, which is more or less large, like yes, probably like your thumb. Okay. And I concentrated, even if I considered the whole network for the embedding, I only concentrated on the nodes, on the brain regions of the temporal lobe epilepsy. So first of all, I did an independent embedding of each layer. In this case, the layers were layers of patients. The multi-layer of patients had 19 layers, and the network, the multi-layer network of healthy subjects, had 28 layers. And you can see that in red are those nodes of the temporal brain areas from the patients are completely mixed on the projection with those nodes of the same temporal brain areas from healthy subjects. So you cannot distinguish it very well. But what happens when you use our approach? You can see that all the nodes of the brain temporal area from patients are relatively well concentrated, are not the same in the same position, because of course each network is different, but are relatively concentrated, and of course are different from those nodes of the healthy subjects. why, probably you are wondering, why there is a group of nodes, healthy nodes, that are close to this? Because I mentioned it, the patients that arrive in my hospital, they are very heterogeneous. So the lesion is not located in the same position. And some patients have, let's say, we have 3 brain areas inside the temporal lobe. Some of them have only A and B, only B and C, and so or A and C. So probably this separation, this is the sharing areas, brain areas. I mean the brain areas that healthy subjects share with epileptic patients. But at least the most important is that you can observe this concentration that cannot be obtained by the classical embedding method. Now, to arrive to the conclusion, I presented a kind of flexible approach, completely data-driven, for embedding multi-layer networks into hyperbolic spaces. As I mentioned, there are other non-Euclidean spaces, spherical, elliptical, that can be probably a good alternative for embedding your data, especially structured complex data set. Even if you are interested in working on hyperbolic manifolds, there are many other models. There are Lorentz, Klein disk, the D-dimensional Poincaré disk, BAL in this case, half-space model. What is interesting that is you can travel from one space to other through isomorphism. And of course, the representation in neuroscience or multi-layer brain network in neuroscience, you can use to define each layer. You can use different patients, different modalities, temporal networks the limit is your imagination. And I would like to finish by thanking all my colleagues and collaborators, the 2 medical doctors, my 2 former PhD students, my new, he's starting his PhD, and he started 3 weeks ago, Steven. And if you are interested in our works on this representation of brain networks on hyperbolic data, you can check this QR code. You will probably arrive to the homepage of Martin, who has, because in my case, I have papers on ecology, Parkinson, Alzheimer's, sleep, so many other things. But Martin, all his papers are concentrated on hyperbolic geometry. And of course, some colleagues from the University of Barcelona with whom we are developing more, the tools for analyzing this data. So thank you very much for your attention.
Thank you very much. Time for more questions. We have already many.
So at this point, there's a whole zoo of methods like T-SNE, multidimensional scaling, all these things for embedding in usually 2 dimensions, I guess mostly because you want to put a picture in your paper. Yeah. But you do a statistical test on the embedding. It doesn't seem to me like a very honest statistical test because it depends on the embedding procedure you use. So what is the advantage of this against just doing a statistical test on the original time series data, where you can get a real answer whether 2 things are statistically different or not, instead of asking whether or not they could be separated in the plane?
Okay, yes. If you check some of these papers, even if you are here the next week, I will present how we can use this approach for seizure forecasting. So, and the seizure forecasting at least 24 hours before the seizure arrives to the patient. So that you cannot do it if you project the data on an embedding space. So do you have, for instance, no, you cannot. If you're
3 dimensions wouldn't work, 4 dimensions.
No.
It has to be 2.
With 2, only 2. Yep. But it works. And the forecasting problem, it had not been done with what patient, of course, it had been done with 25 patients.
So does that imply that the epilepsy problem you're describing is an inherently 2-dimensional process?
Stop. I never say, I'm here in the camera, I never say that the brain is hyperbolic or the epilepsy is 2-dimensional, never say that. No, again, I repeat it. I only make an estimation that I decide, a projection on a particular space. For in my case, 2-dimensional space seems to be enough. That's
Okay. Quick question on this side.
Yeah, go.
Hi, thanks for the talk. When you say, if you go back to slide 19, you said that at some point you have to go to do a non-linear dimension reduction.
Yep.
And in my part of the world, non-linear dimension reduction screams to me, please use multi-class classification machine learning. Are you using that, or is anybody using that for this particular part of the dimensional reduction?
Yes. The nonlinear dimension reduction, as any other dimension reduction, can be, in the case of the linear one, the classical principal component analysis. This is a problem. Then the classification is something that you do on this. There are two separate, in machine learning, especially or machine learning community, they used to mix the problem. For them, some of them, yes, I projected and immediately I classified. For instance, if you imagine super vector machines, yes, you project in the opposite. You project an hyperspace, a larger dimensional space. You project and you separate, because the functional has been done in this way. I mean, for the super vector machine, the idea is to project in a higher dimension and to separate. This is the only case. In my case, of course, I'm using only the dimension reduction, but then you can add your favorite classification method. Generally, for instance, in my case particular, with my data, simple logistic regression worked very well. So probably there is a rich literature now which is trying to merge in, there is something called geometric deep learning. I'm completely ignorant about, so I know that they try to impose some structure, some connectivity, not necessarily random, but to the classical convolutional networks. So there is a very rich literature now trying to mixing this hyperbolic geometry and convolutional networks, not necessarily machine learning, but it's also hyperbolic super vector machines. But again, then I project and then I plug in a classifier.
Hi. Thanks for your talk. I think that when you are embedding this data, there is a loss of information.
Yep.
And have you estimated maybe with some metrics like information theory or something like that, after applying this, embedding this transformation of data, how is the loss of information? How much is?
Yes. In the case of now, for the people working with clinical or neuroscience data, I don't check it. For me, is, for instance, the objective is to classify something to classes. If it works, I assume that there is an error, but I don't care about how much. Probably it's a mistake. I don't care. I know that the embedding that I'm doing with an error of the projection, but it allows me, probably the error is so small that it allows me to distinguish two classes, to forecast seizures, or to identify, for instance, on other papers with to identify regions associated to Alzheimer's disease. So for me, this is the golden, how to say, milestone. So, okay, to check if I can do this separation. But people working on graph theory, they have measured it analytically. They have estimated analytically the distortion, for instance, when you embed a tree or very sample random networks. Also, you can estimate the error of estimating a random graph, fully random error-range graph, onto a hyperbolic graph. And you can analytically, you can derive it. But in my case, I don't use it. I know that it can be helpful, especially for the patients.
So thanks for the talk. I have two questions. The first one is, why did you choose the hyperbolic space? Is it because some conformal invariance on the network or something? And my other question is, if you can, instead of fixing the space to be hyperbolic, you can learn it in some way to minimize some metric, as you were saying.
For the first question, the honor becomes to Alice Longhena, my former PhD student. She's Italian, and she comes from physics, and I don't know why, she was very interested in gravitational theory. So when she started, she said, Mario, but gravitational hyperbolic, something hyperbolic, have you tried embedding on hyperbolic space? I said, no, I didn't even know that it was possible. So I started thanks to Alice. So again, camera, if Alice, you are looking, thanks. And for the second is, which was the second question, sorry?
If you can learn the geometry.
Yes. As I mentioned to the previous question, related to the previous question, there are a rich literature where you can use this hyperbolic geometry on learning for different classifiers. I mean, the idea is to, instead of using the classical Euclidean mean square error, you use to minimize a classifier. For instance, the logistic regression that you must minimize a square error, you can minimize an hyperbolic error. And I mean, it's associated to a machine learning. So, but there is a very rich literature on that. So, but you can do it.
Thank you, Mario. Very nice talk. My question is similar to the last one, not exactly, but when you look at your data, let's say your nodes on the brain, then you think on how to embed it, in what kind of a surface. Why didn't, you mentioned that you could have done something like spherical, which will be much easier.
Yep.
And then you deform the sphere for the points. That would be much easier, unless it has something to do, the first one who thought of doing something like this, remember something like how the X-ray data started, and why did they put it in a hyperbolic space?
Okay. Yes, for sure. No, Steven, he's starting, even if he's starting his PhD with me, he was working with me during his university 2 years ago, and we prepared a paper. The paper is already submitted. You can find it in an archive. And we have taken the same data set for the seizure anticipation problem. And we said, okay, Steven asked me, Mario, your hyperbolic stuff is very nice, but have you tried a simpler projection? Okay, no, do it. And he did it. So I invite you to read the paper instead of telling you the end. But of course, I've been working also on a spherical, even if it's nice, the results were not very good. So generally, unfortunately, in science, especially network science, we have the tendency not to publish negative results. I don't know why, because that's a shame. But generally, but of course, we have several negative results with other projections. We say, okay, it doesn't work, put it on the trash and continue to look for another projection.
Thank you. I have a question regarding the slide 17. It's a short question. Why do you expect that in functional networks there could be a separation in the embedding space?
Yes.
Because
an intuitive, I mean, it's not proved with my colleagues in Barcelona and with the clinicians, we have the idea that the anatomical network, I mean, the position of the nodes is already defined in this space, three-dimensional space. Probably the structure of the network inherits something of this geometrical three-dimensional space. Probably, and that's why it's very easy to separate it using an Euclidean projection. Probably.
Yeah, but regarding the functional network, I mean.
Yes, and the functional, there is something very interesting with the anatomical. For the anatomical connection, you don't have very long connection between one hemisphere to the other. With functional, you may have this. So the anatomical connections, the intra-hemispherical connection are relatively short. Never very long range connections. For the functional networks, you may have these very long connections that probably render more difficult the projection here.
Okay, but maybe we can discuss later. Thank you.
Any more questions? You had one? Okay, let's go with the last one.
Okay, thank you for your presentation. And I'm sorry if I got something wrong in the steps, if I didn't follow it right. But in the beginning of the presentation, you were saying a way to encode, to make embedding of the nodes of the network. And at the end, you showed a picture, a plot of the embedding of a graph instead of the nodes. You showed a plot of the patients with epilepsy and the healthy patients. I didn't know exactly how you did the transformation from node embedding to graph embedding.
This one?
Yes.
Yes, there is probably when I say, what I mean by network embedding, for instance, I may have a graph, I don't know, yeah, a given graph. Network embedding can be misunderstood by I project the whole graph as a single point in a given space. This is not what I mean for. What I mean is, I understand by network embedding is the representation of each node of the network. Probably it's an abuse of language that...
Could you explain further this last plot? Because as I imagine, each node is a patient, yeah?
Yes.
And each patient has its own network, its own graph. And I mean, you're plotting like a single node as a whole graph, but in the previous slides, you were embedding or plotting each node in its embedding space, latent space.
I understood the question. So imagine I have a very sampled network. This is for the patient 1. This is for the patient 2. Let's say only very sample for 3 patients. Okay, patient 3. This is the whole network, the whole brain. I project, this is the layer 1, the layer 2, and the layer 3. I embedded, I project them, but I only, on the projection, of course, there should be 5 nodes per patient. But what I was saying was that I only concentrate, I took into account only the nodes of the temporal brain areas. So I only keep the position of the nodes that are in the temporal brain areas. The position of the others, I didn't care. That's why.
Okay, so in this particular plot, each node is not necessarily a single patient. It can be more than one region of each patient. Okay, thank you.
Okay, so I think we can thank our speaker again.